Thank you for the introduction. This is Suzuki from Institute of Science Tokyo. This talk is a continuation of our work in progress paper presented in the last year's MPLR. Recent microcontrollers have powerful processors and memory resources to meet the requirements for IoT applications. However, such powerful resource costs higher power consumption. Therefore, modern IoT SoCs like the ESP32C6 are equipped with a low-power coprocessor or LP coprocessor. It is there to handle simple and long-running tasks on behalf of the main processor. The LP coprocessor can significantly reduce overall power consumption. However, this power efficiency comes with limitations. For example, the LP coprocessor cannot access high-speed peripherals like SPI. More importantly, it has access only to a limited amount of the memory. On the ESP32C6, only 16 kilobytes of memory is available when the main processor is asleep. These constraints introduce several major programming challenges. First, our target LP coprocessor has no memory protection unit. This means that memory safety is not guaranteed by hardware. On the ESP32C6, accessing an invalid pointer can result in corrupted data or even freeze the LP coprocessor. Second, as shown on the previous slide, the LP coprocessor cannot access the main memory. So developers must manually transfer all necessary data between processors. Third, available memory for code is extremely limited, just 16 kilobytes in our case. This means we must be very selective about the code we place on the LP coprocessor. Finally, the processors can have different ISAs. This is often a deliberate design choice to optimize one core for performance and the other core for low power. However, this increases development effort. For instance, with the ESP32 SDK, a developer needs to write two separate main functions and manage two sets of source code. These are the key challenges we address in this work. To solve the first two issues, memory safety and separated memory spaces, our managed runtime system takes responsibility. It automatically checks pointer validity and moves objects as needed. This frees the developer from manual and error-prone memory management. Second, to tackle the problems of limited memory and different ISAs, we use JIT compilation. The key idea is to generate only the code that is actually executed, ensuring a small footprint and resolving ISA differences on the fly. So in this talk, I'll introduce our solution to these problems. Our goal is to make it practical to use managerial languages on LP coprocessors, with focusing on common IoT use cases like sensing and buffering tasks. Our key idea is a cooperative JIT compilation. In our approach, the powerful main processor handles compilation for the LP coprocessor. It traces the application and compiling only the necessary parts into a highly specialized native code. Then I will also briefly touch on our object management system, and I will show experimental results from our prototype on the ESP32C6. The generated code is larger than C, but the power saving is comparable. Finally, I'll discuss about other languages and related work. Here's an example. This Ruby code reads from a sensor in a loop. With our system, a developer can offload this entire loop into the LP coprocessor with a single copro.run call. This high-level approach has several benefits. For example, object-oriented features simplify the abstractions of different hardware sensors. More importantly, our runtime automatically handles the transfer of necessary objects, like the sensor and result objects. It ensures they are safely accessed on the LP coprocessor. To design our system effectively, we first considered what tasks are best suited for LP coprocessors. Previous research shows that the most significant power savings come from offloading tasks that are simple and frequently executed, like sensor reading and data buffering. In contrast, computationally intensive tasks like signal processing offer only marginal gains, as they tend to run less frequently. Therefore, our experiment is designed for these simple and high-frequency tasks. So why did we choose just-in-time compilation? The main reason is to minimize the code footprint. Managed languages tend to produce large binaries. For example, dynamic dispatch requires Berkeley virtual function tables and introduce to resolve method calls at runtime. Dynamically typed languages add even more overhead with runtime type checks. A naive ahead of time compiler would have to include all possible code passes. It would quickly exceed the memory limits of the LP coprocessor. On the other hand, our JIT compiler allows us to compile only the code that is actually executed. It is suitable for this resource-constrained environment with limited memory. Now, let's dive into how our cooperative JIT works. The core idea is that the main processor and the LP coprocessor work together. The main processor compiles for the LP coprocessor. This aims to reuse the interpreter implementation on the main processor and to use the powerful main processor for the main compilation. I will now explain how JIT operates. This is an example of control flow graph. These cycles are basic blocks. Specifically, I will discuss the operation of copro.run, which is the method for offloading. When copro.run is called, its argument code block doesn't immediately execute on the LP coprocessor. Instead, it begins running in the interpreter on the main processor. As it runs, our runtime traces the execution path. It observes which basic blocks are executed and what data types are used. As the trace proceeds, the JIT compiler generates native machine code for the LP coprocessor. This process is inspired by test-based JIT. Crucially, the generate code is specialized based on types and divided into basic blocks. Because we know the runtime types from tracing, we can eliminate dynamic type checks and resolve method calls directly. This part of our approach is inspired by lazy basic block versioning. When the execution reaches any compiled basic block, it is migrated to the LP coprocessor. The main processor wakes up the LP coprocessor and transforms the stack frames for the LP coprocessor. After the migration, the main processor sleeps and the LP coprocessor runs the compiled code. To reduce migration overhead, we migrate only when the execution reaches any compiled basic block. This differs from an original LBBV approach, where the execution would migrate every time each basic block is compiled. When the LP coprocessor encounters something unexpected, like an uncompiled branch or a variable with a different type than predicted, it jumps to a stub function. This stub function dumps registers to the stack and wakes up the main processor. The main processor then resumes and compiles the new code path and patches the jump to the stub function. Eventually, the execution is migrated again when the main processor reaches any compiled basic block. Next, let's talk about object management. To save memory, we use different object representations. On the main processor, we use a flexible dictionary-like format to support Ruby's dynamic features. But for the LP coprocessor, we convert objects into a compact and fixed layout format, much like a C struct. This saves a significant amount of memory and allows for simple access to instance variables. A key rule in our design is that any pointer on the LP stack has already been validated. This means its referenced object has been transferred and type checked. We enforce this invariant when transforming the stack and whenever reading non-local variables. This is because we gather types from the interpreter and use concrete types to simplify the implementation. The benefit of this approach is that we can eliminate checks on writing to instance variables. In addition, we assume that objects on the stack are likely to be used soon. Therefore, to reduce main processor wake-ups, our runtime moves these objects beforehand when transforming the stack. To evaluate our design, we implemented a prototype based on MLB/C. We tested 4 applications. These applications differ in their tasks and execution frequencies. The simple brightening LED toggles GPIO within a loop. The other 3 applications perform more complex tasks like sorting and averaging. We conducted the experiment with 4 configurations. RM is the original MLB/C, which interprets Ruby on the main processor. RL is our modified MLB/C, which JIT compiles Ruby programs on the main processor and run on the LP coprocessor. CM and CL are handwritten C implementations running on the main and LP coprocessors respectively. First, let's look at the generated code size. The green bars show the generated metadata size on the main processor. The blue bars show the generated code size on the LP coprocessor. The red line shows the code size ratio to handwritten C. As expected, our generated Ruby code size is larger than handwritten C. It is up to 6.6 times larger for the most complex task. This is the main trade-off of using a high-level language. However, it's important to look at the absolute values. Even the largest application required less than 2 kilobytes of code. This is well within the capacity of the LP coprocessor and demonstrates that our approach of compiling only what's needed is effective. Next, let's see the most important result per consumption. The chart on the left shows the power savings achieved by offloading to the LP coprocessors. The key takeaway here is that our approach in Ruby, in red bars, achieves power savings that are nearly identical to the handwritten C implementation in the blue bars. The difference is negligible. The chart on the right side shows the JIT overhead. We can see higher power consumption during the first few iterations because the system compiles code and moves objects. However, the system quickly stabilizes into its low power state. For any long-running IoT application, this initial one-time cost is easily amortized. Finally, let's look at the runtime size. The original MLB/C runtime is over 40 kilobytes, which is far too large for the LP coprocessor. On the main processor, our modified interpreter is about 35% larger than the original, mainly due to the addition of the JIT compiler logic. Our runtime for the LP coprocessor, including the GCC and the stub function, is only 5.2 kilobytes, easily fitting within the 16 kilobytes memory. Finally, let's discuss how our cooperative design could be adapted to other languages. First, let's consider languages like C and Rust. A key challenge here is object management. Even though these languages don't have GCs, our system would still require runtime checks before every memory access. This is to handle the movement of objects between the main and LP memory spaces. Next, what about the statically typed languages like Java or C#? For these languages, a technique like lazy basic block versioning might be less critical because of fewer runtime checks. However, the fundamental challenge of object movement between separate memories would remain. Therefore, we believe that our approach of dynamically loading code and data is still a very feasible and beneficial approach even for these languages. There is related work targeting server systems or rich embedded systems, such as Android. These three works are close to our work compared to systems like Reflex. Our approach is tailored for manager languages and doesn't require manual locking, because Reflex assumes that the processors work simultaneously. So it serves software-based distributed shared memory, and developers need logs for shared objects. Unlike transkernel, we compile application bytecode on the main processor, not kernel binaries on the LP coprocessor, and performs specializations based on types. Sidewinder focuses to wake up main processors by an LP coprocessor. It lacks flexibility because they provide only predefined APIs and hardware. This makes it difficult to use various sensors. In conclusion, we have addressed the challenge of using high-level manager languages on resource-constrained low-power coprocessors. We proposed a cooperative JIT compilation design where the main processor generates specialized compact code for the LP coprocessor. Our experiments shows that this approach makes it practical to gain the productivity and safety benefits of a managed language while achieving power savings that are comparable to C implementation. Thank you.
For questions.
Okay, so thanks for interesting talk. So I'm wondering how difficult is it to create such just-in-time compilers?
It takes 1 year and a half. So I think debugging garbage collector is more difficult than JIT compiler because
oh my gosh, thanks so much.
Yeah, because no memory protection unit.
Can you comment on the time it took to build those JIT compilers?
No. No.
So how much time was it? How much effort? How much effort was it for you or your team to build the JIT compiler?
Well, 1.5. 1.5 years.
How long was this lines of code you wrote for
Code.
just-in-time compiler?
Oh, I will check later.
Okay.
Sorry.
Answer offline. Always a good response. I'll talk to you offline. Best answer to the question.
Thank you.
Okay, so are there any further questions? Okay, if not, then let's... yes, here we have one. Okay, thank you.
Thanks for the interesting talk. I remember that you mentioned you use like a tracing JIT compiler to generate code for the low-power coprocessor, right? But then my question is that what if, as you mentioned, like the main processor and the low-power coprocessor could have different architecture, then apparently tracing JIT won't work. So how do you solve this problem? Do you have some sort of like intermediate representation too?
In our implementation directory translates MRB bytecode to RISC-V, and the generation of code is performed by directly writes instructions by hand. No, not like Python.
Okay. Thanks, I got my answer.